And is to join Patrick Moore on a transatlantic trip to see the world's largest refractor telescope in the sky at night.
I am standing in the doorway of a most impressive building. As a piece of architecture, it's well worth seeing. But it's more than that. This is the Yerkes Observatory at Williams Bay, 76 miles from Chicago. It's an old observatory, dating back nearly 100 years now, and in many ways it's unique. It was the brainchild of a most remarkable man, George Ellery Hale. Hale began his astronomical career as an observer of the sun, and he had his own private observatory equipped with a 12-inch refracting telescope. But he was also very interested in what we may call deep space, and he realized that for that kind of work, you need a telescope of immense light grasp. By sheer chance, he found out that in France, there was a pair of glass blanks that could be turned into a 40-inch lens, and a 40-inch refractor would be far more powerful than anything previously built. But of course, it would also mean a great deal of money. Hale was well off, but not so well off as that. He needed a friendly millionaire, and he found one, Charles T. Yerkes, a Chicago businessman. And after a great deal of persuasive sales talk from Hale, and Hale was very good at that, Yerkes finally agreed to put up the money to build this observatory. When the observatory was complete, it was the best and most up-to-date in the world. But the dedication didn't pass off entirely without incident. One of the many trustees suddenly realized that on the columns there was a design of a bee about to sting a man. Most undignified. That wouldn't do at all. And anyway, there's a suggestion, whether true or not I don't know, that it indicated Yerkes about to be stung for the money. So a mason was called in and solemnly chiseled off 96 bees. And you can still see the marks where the bees used to be. There is one of them. And while we're on the subject of silly stories, there's another concerning the second director of the observatory, whose name was Frost. And this is a method of finding out the temperature without looking at a thermometer. In some months of the year, there are plenty of crickets around in the observatory grounds, and what Frost did was to count the number of chirps made by a cricket in 13 seconds, and then add 40. And that gives you the temperature in degrees Fahrenheit. And I'd love to demonstrate that, but at the moment, I'm afraid, it's the close season for crickets. Now let's go into the dome, where Richard Dreiser is showing the 40-inch to a group of visitors.
The telescope tube is 63 feet long and weighs approximately 20 tons. It's made of cast iron, and it's designed so it can be moved in either direction from north to south or east to west. At the top end of the telescope tube, underneath that blue box, are two lenses. These two lenses are separated by about 8 inches of air. The light-gathering ability of the lenses, which is very important in astronomy, the lenses gather approximately 36,000 times more light than the human eye is capable of. The lenses focus the light 63 feet down to this end of the telescope tube, the eyepiece. Now, the entire dome rests on 26 wheels, and I can rotate the dome in either direction so that we can look anywhere in the nighttime sky that we want to see something. The dome is not only very large so that the telescope tube can rotate and not hit the ceiling, but it protects the telescope from the elements. You may have noticed that the telescope is way above my head. The eyepiece of the telescope, which is what the astronomers would look through, and it's what is removed when the astronomers wish to take photographs, is about 8 feet above my head. In order to get underneath the eyepiece, no matter where the telescope is pointing, the astronomers raise the entire floor. Right now, I'm standing on an elevator which weighs 37.5 tons and is 75 feet across. In a moment, I'll be turning on an electrical motor in the basement. The motor will lower 4 sets of very heavy weights, which are connected to the floor. These weights and the cables which hold the weights up are the only thing holding the floor up, all 37.5 tons of it. And if you watch carefully, you'll be able to see the floor shifting back and forth very slightly. Right about now, when I turn the floor motor on, those green weights that you see around you will begin to move down over very big pulleys, and the entire floor will move up like this. You may get the feeling that you're moving down, but in fact, I'm moving up, and you can see that I'm getting closer and closer to the telescope. You may wish to stand up at this point, and if you're under 4 feet high, you may want to stand on your chairs, but please keep away from the balcony. Notice that the control panels have hooks on them so that we can hang them onto this circle on the end of the telescope. Right now, we can see the eyepiece of the telescope tube. By turning these knobs, we can actually remove the entire eyepiece. This creates an 8.5 by 11-inch opening at this end of the telescope into which we can put a negative carrier which holds a single glass negative. By putting in a single glass negative at this end, we can take long time exposures, sometimes lasting a few minutes in length, sometimes lasting up to 3 or even 4 hours. Another thing that's very important is actually moving the telescope. Right now, the telescope is pointing somewhat to the south. But by turning on one of its electric motors, I can swing it around so that it's pointing to the north. And this is something I'd like to show you. Here is the control panel, which allows me to move the telescope, in this case, to the north. Now, the entire telescope actually weighs about 20 tons, but it is so finely balanced because of the brown weights at this end that it can actually be moved by hand fairly easily, which is what I'm doing right now. In fact, it's possible to raise the floor and hold the telescope and push the telescope as the floor goes up, like this.
The present director of the observatory is Dr. Al Harper. Yerkes has a fascinating history, but there was nearly a disaster at the very beginning, wasn't there?
Yes, the large rising floor and the 40-inch refractor crashed to the ground in the middle of the night due to a design flaw in the elevator mechanism, and it came crashing down about 10 minutes after the night assistant had just left the telescope. Unfortunately, no one was hurt, and except for a slight delay when they reconstructed the floor with a more rugged design, there was no impact on the operation of the observatory.
The 40-inch refractor itself was designed originally for visual use, but the main emphasis here has always been on astrophysics.
Yes, although the parallax program and proper motion program for measurements of positions and motions of stars has always been a central element here at the Yerkes Observatory because of the unique suitability of the large refractor for that kind of work. George Ellery Hale conceived of the Yerkes Observatory as a complete astrophysical observatory which would conduct a very wide range of activities. Also, the observatory was designed with a full complement of optical and machine shops and laboratories down in the basement for the construction of new types of instruments and new types of telescopes. One of the things that's of particular interest to me as an infrared astronomer is that the first measurements of stars and planets at infrared wavelengths were conducted here by E.F. Nichols in 1898. He came at the request of Dr. Hale to put his newly developed radiometer at the focus of a specially constructed telescope which was erected in the solar telescope room up on the second floor of the observatory. And with this special facility using the new 2-foot diameter mirror ground by Ritchie in optical shops here, they detected Jupiter and Saturn and Vega and Arcturus. It's taken quite a while to follow up on those observations because of the long lag in the development of sensitive infrared detectors, but that's a large part of our program now.
It was George Ellery Hale who, in 1892, founded the Department of Astronomy at the University of Chicago, of which the Yerkes Observatory is an integral part. From the beginning, this was an astrophysical observatory. Two very important programs concerned stellar parallaxes and proper motions. The parallax of a star is its apparent motion in the sky over a period of a year due to the real revolution of the Earth around the Sun. Proper motions are the genuine independent shifts of the stars relative to each other. Both these programs are carried on here with all the telescopes, including, of course, the 40-inch refractor. And one of the astronomers who knows the telescope well is Kyle Cudworth.
The 40-inch has a number of advantages. The biggest is that it has been producing excellent photographs, good images, ever since it was put into operation in the 1890s. There have been good photographs taken starting in 1900, and the work that I am doing involves comparing these old photographs with new ones. And therefore, the great age of the old ones is an advantage. We can see how things have changed over a long time base.
Most of the plates taken over the last 90 years or so are stored right here in the plate room. But I gather that they're now being re-enveloped.
That is correct. The plates have, over the long history of the observatory, there have been probably over 100,000 plates taken, of which close to 30,000, I would guess, are stored in this particular room. And for many years, they were stored in rather poor facilities upstairs. Then, in the 1970s, this new plate vault was built, which is air-conditioned, good temperature control, good humidity control. We also are gradually going through and re-enveloping the plates, taking them out of the old envelopes, which often reacted badly with the photographic emulsion, and cleaning the plates and putting them into new envelopes that should be very good for archival storage of the plates.
But of course, although there are plenty of old photographs, but I suppose the great advantage here is that these have been taken with the same telescope.
That's right. The fact that they are from the same telescope, and so any differences that we see between the old plates and the new ones are almost certainly due to things that have changed out there in the sky, rather than due to something different in the optical system of our telescope. Here we have the plate of the globular cluster Messier 13 that I took a few years ago with the 40-inch refractor. We're comparing it here with another plate taken of the same cluster, taken with the same telescope, but taken in 1901. The exposure in 1901 was a 3-hour time exposure. The new plate taken just a few years ago illustrates how much more sensitive modern emulsions are, in that this one goes a little bit fainter, but it only required a 1-hour exposure. And actually, that comparison is being made against an old plate that was more sensitive than the typical plate used in 1901.
A lot of your work with the 40-inch has been on stellar proper motions.
That's right. Proper motion is the angular motion of the star, which we measure by comparing an old and a new photograph. And the Yerkes refractor has been great for this because we have so many excellent, very old photographs. We have a long time base for the proper motion of the star to build up, to see the changes over this long period of time. And in particular, I've been working on proper motions in these star clusters.
What does this tell you about the dynamics of the clusters?
Okay, from the stellar motions, we're able to really look at how each star is moving in response to the gravitational pull of all of the other stars in the cluster. So you've got a mass of maybe close to 1 million stars in this cluster. Each of those stars feels the gravitational pull from all of the others, and you can see, by comparing the old and the new Yerkes plates, see the very small motions of each star responding to that gravitational pull. And from those small motions, we can derive how strong that gravity is, thus derive the mass of the cluster.
What about the future plans for the 40-inch?
Well, there are a number of additional clusters that I want to continue this kind of work on, both the globular clusters, the extremely old and very dense clusters, but also doing some work on some younger clusters, open clusters. There probably will be a parallax program using modern electronic instruments put onto the 40-inch within the next few years that will allow us to do parallax work, measuring of distances for fainter stars than we have been able to do so far.
Using special equipment attached to the 40-inch refractor, W. Morgan made a discovery of tremendous importance to astronomy.
I had been working for a number of years on developing ways of getting distances of the very brilliant, the really brilliant stars. They don't look brilliant because they're far away. The brilliant blue stars by taking spectra of them. That is, let the light go through a prism and some lenses until one gets a picture on a plate. Instead of one color, one gets the colors. If one wanted, one could get the colors, but they're all in gray, showing the different lines of the different elements. I just had a feeling, after seeing the marvelous work of Walter Baade, he had taken a photograph, one of the first photographs, really serious photographs with a 200-inch telescope, that had shown the magnificent spiral structure of the Andromeda Nebula. And also, in addition to that, he had taken one exposure sensitive to red light with a filter over it, and there a whole bunch of little gaseous rings suddenly appeared, which would not show necessarily in the ordinary light you see. I modified this method by going to very small scale plates, to where one needed to magnify a lot to even see what was there, but where one could use some kinds of the features to tell, in effect, how big the star was. And we know the color of it, and one can tell how big the star is, and if one knows the color of it, one can tell how bright it is. Candle power, you can call anything you want to call it. Well, this work then was moving. The method then had been developed. And the next thing then was to find these little white little dots or rings in our own galaxy that corresponded to the ones in the Andromeda Nebula. Well, to start with, it seemed practically certain we knew a few of them. We did know some of them because we do have ring-like structures. They don't look as smooth as the ones in the Andromeda Nebula because we see them closer up and they're more detailed. The next thing then was to take spectra of them so we could look and see how bright they were, their candle power, and then from that tell how far away they were. The distance to the center of our galaxy, we're going to call that 10. Then the ones we had here, they were all about 2 in that unit, a whole row. I have here a picture that is somewhat later, but I want to show what I was just been talking about. Here is a diagram. The sun is this funny little thing right here, and this black thing is simply a dark part of the Milky Way. If you look out in the summertime, you can see the Milky Way is divided in the middle with a great big black thing, and that is just a hunk of dirt and that kind of material. Okay. Now then, when I looked at these distances, when I got to the office, it turned out that there were 2 kinds, distances that made it up here and distances that made it like this. In other words, a certain distance away from us, a separation, and then right where we are. All right? This then looked like a piece of a spiral arm, and it looked like we ourselves were living in a spiral arm. Okay?
And that, in fact, is how you originally tracked down the fact that our galaxy, too, was a spiral.
That was the moment of realization, these 2. Yes.
We have a number of telescopes in addition to the 40-inch refractor here. They include a 41-inch reflector, a 24-inch reflector, and a number of small instruments which include nebular spectrograph, which we're currently refurbishing to use for observations of extended objects such as spiral galaxies. We've added a new CCD detector to that, which should much improve its performance. For an extended object and a spectrograph, the critical thing is the size of the grating rather than the size of the telescope itself.
What other new pieces of equipment are you testing now?
This piece of equipment on the table beside me is a new 2-micron camera, which is a prototype of a system that we're planning to build for the new 3.5-meter telescope, which we're constructing in New Mexico, along with a consortium of 4 other universities. Some of the types of objects that we intend to look at with this 2-micron camera would include regions where very young stars are forming and external galaxies, which again may have regions of activity having to do with star formation or very intense sources of energy in the nuclei of galaxies.
Such as M82.
Yes, M82 is kind of a classical example of a disturbed or exploding galaxy. And in fact, that's one of the first things we looked at when we got the 2-micron camera running on the 24-inch telescope here at Yerkes. And in this picture that we have up on the monitor here now, you can see the central red spot is the nucleus of the galaxy itself, and these other sources spread around it are various kinds of active sources heavily enshrouded in this dust cloud. This point source here that shows as yellow, for example, we suspect may be a supernova remnant, which is so heavily enshrouded in dust that it can't be seen at optical wavelengths, but you can pick it up in the infrared. This is another example of an instrument which we've built here at Yerkes Observatory. Although it's possible to make visual and near-infrared observations from even a low-altitude observatory like Yerkes, instrument like this one, which is designed for use at 400 microns, must be used at much higher altitudes, for example, at a site like Mauna Kea in Hawaii. The instrument itself is basically a camera which is composed of a very sensitive array of bolometer detectors arrayed in a 6x6 spatial matrix. It's a rather rudimentary camera by optical standards, where you can have 800 by 800 or 1,000 by 1,000 picture elements. But it's quite an advance over where we were just a few years ago in far infrared and submillimeter wavelengths. Now, at even shorter wavelengths, somewhere between 30 and 300 microns, the Earth's atmosphere completely screens out the incoming radiation, even at mountaintop altitudes, and then it's necessary to go even higher. The instrument that you see down here on the floor, which is broken down because we've stolen the detector array out of this one to put in the submillimeter system recently. This system is a 30 to 300 micron system which we fly on NASA's Kuiper Airborne Observatory. This is a 36-inch telescope mounted in a C-141 aircraft and operated by NASA from Moffett Field, California. In it, you can see the 6x6 array of light concentrators which feeds the detector array. This is just a diagonal mirror which bends the light coming in from the telescope into the detectors.
What kinds of objects are you observing at these wavelengths?
At these long wavelengths, we very often see the radiation from dense clouds of dust which are illuminated by internal sources of illumination, which might be protostars, stars in the process of forming, or in the case of galaxies, by very energetic clusters of young stars forming in, again, large dust clouds. You perhaps recall the picture of M82 that we had the other 2-micron instrument. At far infrared wavelengths, we'll be seeing the dust clouds which are obscuring the 2-micron radiation which we saw in the other picture.
When we first came here, I said, and I say again, that in many ways Yerkes is unique. At first sight, it may even look a little old-fashioned, which shows how deceptive appearances can be, because, in fact, this is one of the finest and most efficient observatories in the world, and by the very nature of its equipment, it can do things that other observatories find difficult. It's been in action now for nearly 100 years, and I'm quite sure that in another 100 years' time, it will still be where it is today, right in the forefront of astronomical research. Good night.